maybe we'll play again with this in the next class, so I don't want to take up too much time. So let's go back to the MLP, the multilayer perceptron, and the sort of classical argument for why we would not want to use this to process language. I'm not saying this is a correct argument, but we need to have some intuitions for why this might seem like a good argument. So this is true. He's a nice guy. So we have our word vectors here that I'll indicate like this. So we take all the words, and we saw last class that every word in the vocabulary gets mapped to a distinct word vector. There's something called word embeddings. So these are the three word vectors for these three words. I'm going to run these word vectors through an MLP. And we have a slightly, our notation here is a little bit different from what we were saying before. So this is A1, A2, A3. This is H1, H2, H3. And we have a matrix W1 here. Now, can someone remind me of the exact formula? Because there was something funny here, right? Because the inputs into the MLP were themselves vectors. And we had to decide how is an MLP going to process inputs which are themselves vectors. Previously, the inputs, the individual nodes that were going into the MLP, those were just scalars, single numbers. Here we're inputting actually three vectors. So what was our solution last time? It's not like it's the correct solution. It's just something that could at least, where you can write down math and it's not just gibberish. So what did we do? Yeah. We concatenate all the vectors, right? So we'll say our input vector we concatenate them. The A vector is equal to W1, the weight matrix, times the input vector. H is equal to ReLU of that. And let's say we just have a single output node now, O1. And then we get a probability. So O1 is equal to W2 times H. P is equal to sigmoid of O1. And now we have the probability of that this sentence is positive. So what's the problem here? We were talking about one possible problem last time, which is I think it's a legitimate issue that you could bring up, which is this thing cannot process sentences with more than 3 words in them. Right? We have one input node per word. What happens if you have a 4-word sentence? What do you do with that 4th word? There's nowhere to stick it here. So that's a problem. It is a problem, but it's not really that much more of a problem than what modern architectures deal with. As we just saw, GPT-4 has a maximum context size of 128,000. That's the longest text that you can input into GPT-4. And we'll learn about why basically that is you can't go bigger than that for a model trained in that way. There's a little bit of fuzziness about this, but basically to a first approximation, even modern models have a maximum context size, a maximum text length that you can input into them. So if you told me maybe just for this MLP we need to have 128, it needs to have 120,000 input nodes. Maybe that's right. So that alone, the fact that there's going to be a maximum length, that's not the problem, I would say, or that's not one of the primary problems. It's a problem that's shared by all current architectures. Let's keep thinking about along these lines though. What would happen if I increase the context size of this model, the maximum text length, to let's say 100,000? Well, let's say 100 for right now. Let's just say 100. And I want to make our lives a little bit simpler, and I don't want the inputs. I take that back. Let's keep things exactly as they are. It won't change anything too much. So let's say that I have 100 input vectors into my MLP. So I have W1, this is a vector. W2, this is a vector. W100, this is a vector. And let's say that the size of my hidden layer, that is the number of nodes in my hidden layer, let's say that stays the same. So that stays at 3. So I have A1, A2, A3. So let's go back to the actual math that this represents over here. So what's my input now? My input is going to be the concatenation of all 100 vectors here. Oh, should be concat of this. And then I have A is equal to W1 times input. So what can we say about the dimensions of W1? So W1 is a matrix. A what by what matrix? Yeah. Okay, so number of hidden units. How many hidden units are there? 3. Okay, so it's 3. So 3 rows. How many columns? The whole length of this input vector. But can you give me a formula for that length? So let's say the dimensionality of W1 or any of the any of the input vectors. So we have each of the input vectors. Let's say this is W1 is 300. Maybe it's 100, maybe it's 300, maybe it's 1. It almost actually doesn't really matter for us right now. It's some number, and then we have to multiply that by 100. So how large is this matrix here? That is, how many numbers are inside of this matrix? Yeah. Right. So it's going to be 3 times 100 times the dimensionality. Now let me note one feature of how people actually build their neural networks in practice, which is the number of hidden states here is not going to be 3. It's usually actually equal to approximately the size of your input vectors. So if you have if W1 is of dimensionality 100, probably you're going to have around 100 hidden units there. Why is that? Because if you don't, then you're losing a lot of information basically. You're going to be projecting down into a much lower dimension, and so you lose a lot of information about your input. So people don't want to do that. So in practice, it's not like a hard and fast rule, but to within an order of magnitude, this is going to be basically the dimensionality of your word embeddings. I'm choosing W1 here. Whatever your word embedding is, it's going to be approximately the dimensionality of that. So now the size of W1 is equal to the dimensionality of your word vectors times 100 times the dimensionality of your word vectors. So you have dimensionality of your word vector squared times 100. So this part is, you see something that's squared. That maybe is not great. That's inevitable though. Okay, so that's like all neural architectures that work are going to have something that look like this. That is, if you have an input, generally that input gets mapped to something with this approximately the same dimensionality. You don't want to make the dimensionality of the output too small, or else you lose information. So this square, what it means is just that you basically, most neural networks consist of like matrices that are approximately square. That's why you have this quadratic here. Okay, what about this 100 though? Where did that 100 come from? It's actually the maximum number of words that you want to input. It's not the number of words in a particular text. It's you're designing your architecture to handle a maximum size length, maximum length input. That's what the 100 is. Okay. So what happens if we want to update our architecture to handle texts of length 100,000? So we have W1, W2, all the way up to W100,000. Oh, should be. Give that one an extra big circle. What happens to the size of W1 now? Our weight matrix. How many numbers does it have in it? What's that? 1,000 times more than the original, so it's going to be 100,000 times the dimensionality of your word embedding squared. So let's write the same way as over there. So dimensionality of W squared times 100,000. So that's 1,000 times more than our previous. And let's get a sense for how what these numbers look like. People routinely use, a small-ish model, not very small, but small-ish model these days. Dimensionality of your word embeddings. So this is dimension of word embeddings. Let's say it's around 1,000. That's not a big model. It's way smaller than GPT-4. Let's say it's approximately 1,000. So that's 10 to the 3. So that implies size of W1 is what? So that's going to be 10 to the 3 squared times, and what's 100,000 is 10 to the 5. So that's 10 to the 11. So this is for a not very large, like word embeddings are not very large. You're going to have 10 to the 11 parameters in just this single weight matrix. 10 to the 11. What number is that? 100 billion. So that's the entire size of GPT-3. One of the largest models that's ever been trained. So this is one of the major reasons why people do not use MLPs. It's because the size of your weight matrices increase linearly with the length of the maximum length of the sequence that you can allow. And it leads to absurdly large weight matrices. Again, this is only for directly processing the inputs. Deep learning is about deep models. That is, models that do many, many, many layers of processing. So you don't want almost all of your weights to be in the lowest level of the model. You want your weights to be spread out among the first layer, the second layer, the third layer, the fourth layer. Here you're building a GPT-4 size model just to do the first level of processing. So that's a disaster. A lot of decisions in deep learning come down to just considerations like this. It's not like we're not thinking very hard right now, right? We're doing simple arithmetic and just seeing what happens if we decide to do something. Any questions about this? Okay. Yeah. Right. Oh, great. Okay, great. So where did this 100,000 come from? Or yeah. Aha. So dimensionality squared comes from the fact that so this is our hidden layer, right? So this is our first hidden layer. So when we project down from we're mapping from the input vectors to a hidden layer, and generally people want the size of a hidden layer to be approximately the same size as the individual word embeddings. Yes. Yeah. So it's 100 billion parameters to process. Just do this level of processing. Just matrix W1. Yeah. No. This is just to do input. I mean, this is like you want to build like the way that people think about the size of models is usually basically the size of the embedding vectors, because the size of the embedding vector basically determines the size of your hidden states later. Like you could choose it otherwise, but that's what works best in practice. So to train a not particularly large model in the sense that your word embeddings only have 1,000 dimensions, you need to build a 100 billion parameter model. That's what we just learned, which is crazy. Any other questions about this? Okay, so that's one reason why. I mean, we basically like look. I gave some math here that gives some intuitions, hopefully. But like high level idea is just if you have an MLP, your weight matrix has to get bigger and bigger and bigger as your sequence length increases, and it gets ridiculously big very quickly if you do this. There's another reason why, and I'd say it has more to do with like linguistics. Why many people thought, and I'd say almost most people in the field still think MLPs are a bad idea. Yeah, word order is fine here. Actually, but let's talk about that. It's a great question. So what's your concern about word order? Great. So that's a great observation. When we're doing the concatenation here, we absolutely are preserving the order in which these words arrived. And the model will know about word order. Why does the model know about word order? Like, where is that information represented? The fact that like I came before like here. Like, how can the model know that? Yeah. Exactly. We have different weights coming off of the first word and the second word and the third word and so on in the sentence. So each distinct word location contributes differently to each distinct hidden state. So that's how the model will keep track of word order. Word order actually something that MLPs do great. It's actually, the way I would actually think about this problem, it is related to word order, but it's actually almost the opposite. Good. Yeah. I mean, you're training the weights based off of the position in the sentence. So if you have I like coleslaw and you're trying to capture some like relation between like and coleslaw, but if you insert say I don't like coleslaw or I really don't like coleslaw, then it's fantastic. That's exactly right. So if I change the position of I don't like coleslaw, so W don't, we get the idea. So I'll just write it in here. So if I change the position of the words, any word in the sentence, then basically all words that come after that, they're now at a completely new location, and the weights that they touch are now completely different. So previously we had I like coleslaw. Like touched this particular set of weights. Coleslaw touched this particular set of weights. When we shift the word just by one word down, they see a completely new set of weights now. Those weights, like, imagine we're only training on a finite amount of data. There are going to be all sorts of combinations of words in our data that we never got to, or there are going to be all sorts of combinations of words that we never got to see in our data. If you present the MLP with something that it hasn't seen before, there's no reason necessarily to think that it will be able to generalize. It's like the weights that will be touching each word are potentially completely unrelated to the weights that touch those words in the training set. Another way of saying that is it's not clear where in the model you can represent the similarity in like I like coleslaw and I don't like coleslaw. Those are almost the same sentence, right? They mean almost exactly the same thing, except like one is sort of positive, one is negative, but the meaning is sort of the same. It doesn't seem like there's anywhere in the model where that sameness or that similarity could be represented. You just have two completely different representations for those two sentences. And that's a consequence of the fact that each input word gets its own set of weights. Each input location, I should say. So this is a sort of theoretical argument. I would say that let's say like a little bit more about this. So like, what are the types of ways that we can sort of superficially alter sentences while retaining a lot of similarity in meaning? So you can insert things like insert like really or don't. So like insert qualifiers. You can insert adjectives, right? Like I like yummy coleslaw. What else can you do? Where you end up shifting the positions of the words, but retaining a lot of similarity. Yeah. Okay, right. So contractions or not using contractions. What else? Yeah. Okay, sure. Qualifiers of various sorts. So not adjectives necessarily, but qualifiers, like the coleslaw that they have at the store, or maybe something like that. Yeah. Yeah. So can you give an example of that? Or, exactly. Yeah. I, student of lign167, do not like coleslaw. Good. Okay. So relative clauses. Another case would be embedding. Like if I don't like coleslaw, then I'm not going to like this party because obviously the party all they do is they serve coleslaw. Embedding the sentence in various ways. So there's lots and lots of, I'm just kidding, this is just a case, there's lots of these things. There are lots of ways of basically creating new sentences out of old ones that basically preserve the meaning of the old sentence but shift the words around in various ways. There's Yoda talk, right? Coleslaw, I don't like. Or no, that's not quite Yoda, but like there's like ways of shifting around, like word order means the same thing. The neural network will not perceive those sentences the same way though. So this is the classical argument for this. People found it persuasive. There's not very, very strong, I'd say, empirical evidence against it yet. My prediction, though, is that this argument, I always used to give this argument like, very confidently in previous years. It's too soon to call it, but I think my guess is that this argument is not going to hold in the future. I think there are going to be architecture. I think the future basically looks like every word position learns has sort of its own set of weights, something like that, and it doesn't matter. Because what what I'm saying right now is that the MLP, another way of saying this is that MLPs do not have good inductive biases. We want architectures that have good inductive biases. What is an inductive bias? Inductive. So for many people in machine learning, biases are a good thing. You don't like bias, but machine learning researchers traditionally have liked bias. Why? Bias means basically information that the model has before you even start training it. Why do you want to put information into your model? It's so that it learns more easily. So that some patterns that actually occur in the world, those are easier for the model to learn. That's what many machine learning researchers have traditionally liked. So I would say the traditional idea, build systems, build models with good biases. So this is the traditional argument. We want to build something into our model that says, like, word order matters, obviously, but it should not matter this much. You want information to be shared across different positions in a sentence or in a text. The problem is the entire history of the field is about taking models, removing inductive biases from them, and getting improved performance. There's nowhere in the field, basically, where inductive biases have helped. I mean, the trajectory has been just taking existing models and stripping out anything that looks like an inductive bias, seeing much better performance. I think that's what's going to happen here. Has not happened yet. One of the major reasons why it has not happened yet is this problem. The weight explosion, the fact that you get so many, if you use an MLP in a very straightforward way, your model is just so huge. So we have to figure out a way to get rid of that problem while maybe keeping the low inductive bias of the MLP. That's my prediction. But so that's like, but basically, so what's the rest of this course going to be? It's going to be various architectures that go beyond the multilayer perceptron and that actually solve both of these problems together. And there are different approaches to this. So the first architecture that we're going to be talking about is the recurrent neural network. And it is interesting that basically both of these problems always get solved together. The recurrent neural network solves both the problems at the same time and in the same way. Transformers do as well. And let's see how recurrent neural networks do it. And by the way, so when I was talking about this problem about word order, it doesn't only apply to single sentences. I mean, it used to be the case that these models basically looked at single sentences, but that's obviously not true anymore. They process entire books. So when you think about it from that perspective, this problem of like shift invariance, that's something like that's what we want. That if you move like words in the text to the right, the meaning doesn't change very much. At least it's not perfect shift invariance, it's approximate. What's the issue that you encounter if you're processing a book? It's that a sentence on page 1 probably means approximately the same thing as the same sentence that appears on page 50. Maybe not exactly. There can be some wrinkles there, but to a first approximation, it means the same thing. These models, NLP obviously does not capture that in a straightforward way. So let's talk about these two properties that we want. I'll call them two good properties in quotations because maybe one of them is not so good, but this is the perspective of the field. So one will be slow or no growth of model size with increasing sequence length. So as you have longer and longer text, your model does not grow linearly with the length of the text. So then the second property is approximate shift invariance. So again, you don't want perfect shift invariance, but something that's like not completely as variant as an MLP. So we're going to start talking about recurrent neural networks, RNNs. And RNNs are very interesting because this used to be what everyone used until 2017. Everyone used RNNs for processing language. There was nothing else, basically. Then 2017 came transformers, and transformers are all of your favorite language models are still transformers. I mean, we're going to learn about transformers after RNNs. But the very interesting thing is that RNNs have some properties that are nice that transformers don't. And there are new architectures that basically combine the best features of transformers and RNNs. So they're not transformers anymore. Now, that's not what GPT-4 is. Also, this is. I feel like I'm missing something, right? The AC went off. Is this the first time this quarter this has happened? Or yeah, okay, I'm gonna have to get used to this. Okay. So transformers are not like the end all be all. We're going to see that probably we'll probably see this even now. Like RNNs have at least one very very important property that transformers don't. And so it would be great to have models that combine these things. So how should we start? Okay, this is freaky. So yes, it's really quiet. Okay, let's do this over here. So we have a sentence. And what we'd like to do is process this sentence and get basically a representation of what this sentence means. So that's going to be our ultimate goal. It's going to be to take in a sentence like this, or a phrase like this, turn this into a hidden state, turn this into basically a vector, and then we're going to use that vector for something. And MLP does this, right? The MLP that we had turns sentences into vectors that then we use for classification. Right, so we have a vector, we map it into one of those output units. We run that through a sigmoid, gives us back a probability. We want to do exactly the same thing here. So we want to have a function that turns sentences like this into vectors. In RNN, we're going to learn about one type of RNN right now. It's a particular strategy for doing this. So what does the RNN do? I'm going to give a very, very sort of simple example of this. Okay, so what the RNN does is it processes words one at a time. You feed the word into a function, you get a hidden state h1. You take that hidden state h1 and you combine it with the next word. That's going to give you a hidden state h2. You take the hidden state h2 and you combine it with the next word. That gives you a hidden state h3. How many people here have worked with Markov chains before, hidden Markov models? Okay, so maybe not that useful. Okay, but maybe they're not even teaching this anymore. So it's very reminiscent, at least, of a sort of classical classical modeling approach that people use called the hidden Markov model. Not exactly it, but very, very closely related to it. So let's write down some math and we'll see how this goes. But again, the basic idea is that we're going to be processing these words one at a time and feeding the past results of our processing into the next state of processing. So we have, this is our initial hidden state. How do we choose this thing? We can just randomly initialize it. We just randomly choose an initial hidden state. Okay, what's h1 equal to? Let's give a formula for h1. And again, I'll assume that we've transformed all these words into word vectors. That's always going to stay the same. So whenever we have a word, we have a lookup table that says, what's the word vector for this? This is W llama. This is W red. This is W pajama. Has anyone read these books, by the way? No? They're like on the less annoying side of toddler books. There's some nice things about them. So if you're in a situation where it's useful, you need to read toddler books for whatever reason, recommend it. Yeah. Okay, fantastic question. So this is a choice that you have when you're building a tokenizer. So a tokenizer is something that we talked, I guess, a little bit about tokenization last time. I gave a very, very simple type of tokenization where each distinct word in your vocabulary gets a distinct vector. This is it's just another choice that you can make. It's another hyperparameter, in fact, for your model. That's how people think about it. Another knob that you can tune before you start training your model. So what are the advantages of choosing to represent capitalized and uncapitalized words separately, and what are the advantages of choosing to represent them combined? Yeah. Yeah. Oh, okay. Well, so almost none of those will actually appear in your corpus to a first approximation. So you don't have to, if it doesn't appear in your corpus, you can't learn it, so you can just throw it out. So you have two for each one, right? So what are the consequences of that? Exactly. So your embedding matrix is not twice as large. That's one consequence. Let's think about learning, though. So okay, so if you don't capitalize, so if you do capitalize it, then you can keep track of someone who, like the fact that someone decided to capitalize something in one position in the sentence. That can be important. It can tell you whether something is a name or not. Like maybe there are some examples of this, of words that can be names, but if not capitalized are not names. Does anyone have? There's one example I can think of that's not appropriate for this class. Yeah, go ahead. Oh no, that's not the one. I mean, it's a little bit. I mean, not my favorite example, but it's a legitimate example. Yeah, look, AIDS capitalized versus not mean very, very different things. So if you decide to collapse those two things together, maybe you can use the rest of the context to figure it out. But like your model now has to do some work to do this. Was there another example? Yeah. Great, Bell. Yeah, last names are a lot easier. You're right. Yes, Bell means something different if capitalized. Great. So in general, if you decide to collapse these things together, you lose information about the text. Like one principle that is a very good principle for tokenization, or almost anything to do with processing text, is you want to keep around as much information about the input text as possible. Because if you don't, then your model can't use that information. It's just not there. You can always throw out information. There's no way to like put back information that is lost. On the other hand, there are disadvantages besides the weight matrix issue. It's related to the weight. You're doubling your weight matrix size potentially. You're not actually going to double it because most words won't appear capitalized in your text, and you don't need to worry about it. But there are some disadvantages beyond that issue to having separate vectors for capitalized and non-capitalized. Yeah. I think that you're on the right track, but I would put the sort of emphasis on a different part of that. So you're right. You're going to have, for many words, not Bell, lowercase and capital Bell might be very, very different because one's a person, like one is a physical object, like not a person. So those vectors will actually be quite different from each other, I expect. But yeah.
And for some things, you're going to get like no training, just not know what to do. And like, I'd imagine llama doesn't very often appear capitalized like at the beginning of the sentence, where llama is not usually there. So you can see that.
okay, great. So you're going to run into data sparsity issues where now you have all these capitalized words that you only saw 4 times in your corpus. It's very hard to learn exactly what they mean. I mean, and the broader point here is that there's no more information sharing across, when you collapse capitalized, non-capitalized, you get to share information across these two different like word forms. Now you're saying, no, these two things are completely unrelated. Things that you learn for one no longer carry over for the other. So you have to sort of learn things twice now in many cases. So, so what I would say is that learning things twice is not a problem if you have enough data. So one of the lessons of deep learning is that you should, if you can, you should just learn everything. And that's very closely related to the issue of inductive bias. Whether you collapse these things or not is a form of inductive bias. It's high inductive bias if you do collapse, low inductive bias if you don't. Low inductive bias in general is better when you have huge amounts of data. High inductive bias is better if you don't. Yeah. Yes. So how is basically yes. Although you might think that there's less information being carried in misspellings if they're not deliberate. Like so, what information will be carried is basically information about the speaker and the fact that the speaker is in the context. The speaker is the sort of person who, in this context, would make spelling errors. That does tell you about like what's probably going on in this text. So you will lose information, but it's not going to be the same type of information that you lose, at least, as the capitalization. Yeah. Yeah. It's true. No, you're absolutely right. I'm just saying that the consequences of this inductive bias are going to be different. But you're right, it is an inductive bias, and it will cause you problems. It's probably inferior if you have lots and lots and lots of data. The misspelling one's a little bit subtle because there's so many ways to misspell things, so it's different than capitalization. I think the trade-offs are different there. We're going to talk more about like the details of tokenization in a couple of weeks from now. Oh yeah, that's an exciting topic. It's important, and so we will be talking about it. And so bring up the spelling issues then. We'll come back to that. Okay, but let's discuss formally what this is. I'm going to give an extremely simple version of this. There are many more sophisticated RNNs. We're going to go through the very simplest one. So h1, our vector h1, what's this going to be equal to? It's going to be equal to we'll call it wh, h for hidden, times. So there's different versions of this that we can do. Okay, let's do this version. Okay, so what did we do here? Let's ignore the ReLU for right now. We took the initial hidden state. We multiplied it by a matrix WH. That WH stands for our hidden weight matrix. So any incoming hidden state, the hidden state that represents the previous sentence, previous part of the sentence, we multiply by WH. We add that to our input vector W llama multiplied by a weight matrix WI. So we have separate matrices for processing the previous hidden state and the current input word. And we add those together. We could do something fancier. For right now, let's just say we're adding them together, and then we run the result of that through a ReLU. Yeah. Yes, and that's the key. That's like the defining property of an RNN, or one of the main defining properties. So let's talk about how we calculate H2. H2, what we do to calculate this hidden state, we take the previous hidden state. We run that hidden state, we multiply that hidden state by WH, we add that to the contribution from the current word. So it's going to be ReLU. We take the previous hidden state, which was H1. We add that to WI, the input weight matrix, times the current input, which is W red. H3, our final hidden state. What's this equal to? ReLU, same formula. So we do WH. So we're calculating H3. We look back at the previous hidden state, H2, plus WI times W pajama. So what's going on here? One crucial property, which was already noted, is that it's the same exact weight matrix being applied to the hidden states and the inputs at every single time point. So we've immediately solved this problem. We have no growth of the model size with increasing input length. What are these hidden states doing? Like, what does H1 represent? How can we think about that in the context of this model? Yeah. So far, we've only read llama, and it represents all the information that this llama and before represents. So basically what it knows is that you had one word in a sentence, that word was llama. What does H2 represent? Yeah. Exactly. So H2, if things are working well, H2 includes information about the entire sentence up through the word read. It got that information directly from the word read here, and then as summarized by H1 there. So one way to think about it is that you're sort of recursively taking summaries of all the previous part of the sentence and fusing those summaries with the current word. So H3 gets information from H2 and the Java. So now at the point of H3, we have a single hidden state that represents the meaning of the entire sentence. What can we do with this hidden state? We can run it through a classifier. So let's say we want to do sentiment classification. I don't know if, I guess it depends on your mood whether when you see this phrase that's a positive or negative phrase. We're going to have a special output matrix. So we're going to have O, like O1, our output. Let's say it's equal to WO. I'm going to have a special matrix there, times H3, or times the last word in my sentence. And then my probability, P, it's a probability positive. It's equal to sigmoid of O1. So we do exactly the same thing that we did in the MLP. We have a final hidden state. We run that hidden state through, we multiply that hidden state by a matrix to turn it into something of the right dimensionality. We run that thing through a sigmoid or a softmax to get back a probability, if we want to do classification. Yes? WI, yes. WI for input. Yeah. Yes. Well, okay. Can you take a guess how we're going to get these matrices? Yeah. Where do these W's come from? How do we get them? Yeah. Backpropagation. We have a loss function. We want to classify sentences correctly. We compute a loss. We do backpropagation. And because this is an RNN, the type of backpropagation that we do is a little bit different. It's called backpropagation through time. I think we're going to learn about that next time. Okay. See everyone then.